In this video, we'll build on the fact that we understand the concept of effectiveness factor, and we will learn different aspects of fixed bed reactor design for solid catalyzed reactions. Some of the concepts we will discuss can be extrapolated to the design of the reactors for gas-solid reactions. That we have two reactants, one of them is a gas and the other one is a solid. Now let's first remember what the effectiveness factor was. Effectiveness factor for an isothermal reaction, we denoted with eta. It was the rate of the reaction under the conditions that our reaction is running with a catalyst and we have diffusional resistances within the catalyst divided by the rate of the reaction for the idealized situation where the concentrations of the species are equal to the concentrations on the surface. In other words, where we have no diffusional resistances. And for a first order reaction, this was going to, for first order reaction under isothermal conditions, these rates were equal to the rate constants times the concentrations divided by rate constants times the concentrations on the surface, and the rate constants would cancel, and the effectiveness factor for a first order reaction was a simple ratio of the concentrations. True concentration, which can be a function of position, and the concentration at the surface, that throughout the catalyst pellet the concentration is uniform. Now, this is for isothermal effectiveness factor under isothermal conditions. That these rate constants can be cancelled, right? This is only true for isothermal conditions. For non-isothermal conditions, in other words, in addition to a concentration gradient within the catalyst pellet, if you have a temperature gradient due to the inability of the catalyst pellet to disperse the energy throughout the system, we might have temperature non-uniformities which may change these rate constants and things get more complicated. Under such conditions, we have to solve both the species conservation equation and the energy balance in order to find out the behavior of this reaction within the catalyst pellet. And now we have seen in the earlier video that this non-uniformity in temperature can give rise to reaction domains in the catalyst pellet where we have temperature extremities which may take those effectiveness factors to factors of 10, 100, even to 1,000. In principle, isothermal effectiveness factors range between 0 and 1 under the conditions that the rate constants cancel, under the conditions that our only problem is the concentration distribution. Now, under such conditions of the effectiveness factors, we're also in the conditions of non-isothermal situations, our design is going to proceed as follows. That we're going to take our rate, the true rate, was going to be equal to the effectiveness factor times the idealized rate. What is the idealized rate? Uniformities in temperature and concentration. K times Ca. So this is a very convenient way of designing a reactor. Now, if you know the behavior of your reaction within your catalyst pellet, then you can determine the effectiveness factor by going through the differential equations that describe the physics and chemistry of the problem. You determine your effectiveness factor, and then you obtain a simplified scaled relationship between your idealized rate and your true rate. And between those two, you can just take this true rate, substitute in the design equation of your reactor, and solve for your reactor volume, your residence time, or any other problem that you intend to solve. So far, our concept of reactor design was limited to sizing the reactor. How big is my reactor? And as a result, how can I scale this reactor in terms of material flow rates through this reactor? In other words, what should be my space-time through this reactor? And we have derived the design equations for the idealized well-mixed reactor, idealized plug flow reactor, and we are now going to change our vocabulary, and we are going to design our reactors under non-idealized conditions. Now let's first look at a reactor which is filled with catalyst, and through the catalyst material flows. So I'm going to discuss in this part 4 different models that an engineer can come up with depending upon the hydrodynamics and physics and the chemistry of the system. Now let us take a packed bed reactor or a fixed bed reactor, that the solids are fixed within the reactor bed, and let's see how those solids interact with the fluid going around them, and the solids are our catalysts, fluid is our reactant, and also our product. Now this is our packed bed. And we have a well-behaving solid domain of uniform solids through which well-behaving domain of fluids pass. So our fluids approach here with a superficial velocity of V0, superficial volumetric flow rate of V0, and that superficial volumetric flow rate disperses itself through the channels. And when I say well-dispersed, well-behaving packed bed domain, that we don't have irregularities in the open channels, that the channels are more or less uniform in size and in distribution, and our fluid distributes itself pretty much on a uniform basis. Now, the simplest approach to model this reactor is to take each particle as a cell. Hence, the name of the model, cell model. So we take the whole reactor and we represent the behavior of the whole reactor in terms of the behavior of the individual cells. And of course, according to the position that they reside. Now let us take a slice and take each of those circles that reside within our hypothetical slice, right? So we have a slice of 1.5 to 2 layers of packing material. Now, our plug flow reactor assumption can lead us to comfortably assume that the concentration is in the fluid phase is uniform throughout this slice. So I can regard all those catalyst particles are being exposed to the same concentration throughout. So if I solve the problem for one of those catalyst particles, it means that I have solved the problem for all of the catalyst particles that are in this particular slice. So I'm going to consider that catalyst particle as a cell, and I'm going to model the behavior. Right? I have a cell. The cell has surrounded by a fluid, and I have a boundary layer. This boundary layer is dictated by the hydrodynamics of the fluid phase, and I have transport to this cell by mass transfer. Film on the other side and diffusion on the inside. This transport-based cell model is going to represent my whole problem, and I have already solved a very similar problem when I was deriving the effectiveness factor problem. Now I'm going to get this mathematics imposed upon this cell and then multiply it by the number of cells that I have in the hypothetical frame, which I can regard as having uniform concentration and also, of course, uniform temperature. Now, if I repeat this procedure for each and every hypothetical slice, and of course, the size of the hypothetical slice will depend on the physical system that I'm dealing with. Therefore, it is my engineering that is going to be reflected in how am I going to size this cell domain. Then I can get a good but still an approximate value of how many layers I need for my desired conversion. So this is the cell model. Now let us take another approximation. In the cell model, we have taken the domains are operating independently. They are not interacting with one another. Now let us take pretty much same behavior, a little bit cleaner in drawing. Now, if those domains are interacting with one another, we have to take that into consideration, right? The interaction between the domains are possible when we have partial conversion in each cell. That unconverted material travels to the next cell and conversion takes place in the next cell. So we can define the interaction domains carefully and we can, with that definition of the interaction domains, we can set up subdomains of the reactor where we use our understanding of how a solid catalyst behaves in a field of fluid reactants and estimate the amount of the catalyst we need or the size of the reactor that we need. Now let's take an expanded version of this cell followed by another cell. Now, this cell, in our imagination, takes in a lambda 0 milliliter or microliter per minute of reactants and delivers the same amount, but here we have delta X conversion. So we have X0 here, X1 here. This cell operates and delivers X2. And X is our conversion. Okay? We can argue that this is tanks in series model, and you would be right. The difference between the tanks in series model and our cell model is that we allow for variation in the radial, both in the radial and axial domains. So with that approximation, now I allow for variations also in the radial direction. What kind of variations? I allow for the fluid flow boundary layer to be different, and as a result we have different flow rates going through this reactor at different zones of this reactor. So let us extend our models to domains of systems where we can have variations in flow rate as well as variations in temperature. Now, if this is a non-adiabatic reactor or even an adiabatic reactor, depending upon the thermal characteristics of our reactor domain, it might be highly probable that we have a temperature distribution in this reactor, in addition to a velocity distribution. Now let me draw my velocity distribution of almost perfectly turbulent domain. So this is my velocity distribution in the axial direction, that I have pretty much flat velocity profile, which is complemented by a rapid decrease due to the boundary layer at the walls. This is my velocity profile. In addition, I might have a temperature profile. Let's have an exothermic reaction so that our temperature is increasing when we move closer to the center, and we have apparently externally cooled or heat is dissipated from the walls. Now, in order to account for these variations, we will imagine that this reactor is composed of non-interacting layers, shells, that if I look at the cross-section of this reactor, that I have one central domain, another domain, another domain, and forgive the irregularities, that we wish to have perfectly concentric shells that surround each other. Now when I do that, my hydrodynamics become tackable, that I can deal with the mathematics a little bit easier than if I didn't do so. What am I going to do? I'm going to imagine that here in this shell, which is the same shell as this one, right? It's this shell. It's my shell where my velocity profile is changing, that I have a constant uniform velocity, and that I have constant uniform temperature. Under those conditions of constant uniform temperature and constant uniform velocity, I imagine this shell as a plug flow reactor which takes its fair share of the volumetric flow rate, and then I can determine the conversion in that plug flow reactor. Let me take another slice. This is my second slice. And the second slice corresponds to this domain of my, corresponds to this domain of my cross-section. Now as you imagine that this domain is going to be smaller in volume, hence I'm going to have a shorter plug flow reactor where I have a uniform temperature, a uniform velocity, different residence time, but this uniform temperature is different from the uniform temperature of the other layer. And so on and so forth. So I have converted my reactor with non-uniform temperature and non-uniform velocity distribution into domains where I have uniform temperature and concentration distributions. And of course, this is a model. This is not the real deal. This is a model. Model means that I construct a simplified, I generate a simplified construction of the real thing that represents the real thing. That is a representative of the real thing. Okay? So this is cell model. This is interacting cells. This is a shell model. You're not limited to these models. You can generate your own models if the complexity of your reactor system requires you doing so. So these are just going to give you a starting point of dealing with non-idealities in solid catalyzed reactions, but the bottom line of the problem is that we are trying to divide the problem into smaller pieces where we have a small enough domain where we can take things as ideal, then we can impose upon that small enough domain our understanding of the ideal reactors, and then design our reactor from that idealized situation, and then take and enlarge that to the macroscopic domain.